The H. Bolden Seed Medal is given annually to for outstanding contributions to teaching, research, or practice in geotechnical engineering. This year's well-deserving winner is Professor Liam Finn. Professor W.D. Liam Finn received his bachelor's in civil engineering from the National University of Ireland, his master's and PhD in civil engineering from the University of Washington, and he became interested in geotechnical earthquake engineering, began to specialize in geotechnical earthquake engineering after the 1964 Nagata earthquake. Shortly thereafter, he joined the faculty at the University of British Columbia, where he started the first geotechnical earthquake engineering program in Canada. His research there and consulting interests include liquefaction, seismic response of sites and earth structures, seismic safety evaluation of dams, seismic response of pile foundations, and seismic risk. He's pioneered the use of dynamic effective stress analysis in practice and the use of large strain deformation analyses for the analyses of post-liquefaction deformation of dams. He's published more than 380 papers on geotechnical earthquake engineering topics. In 1999, he was appointed as the first Anabuki Professor of Foundation Geodynamics at Kagawa University in Japan. And he's now an honorary professor of the Metallurgical Institute of Beijing, an honorary international member of the Japanese Geotechnical Society and the Chinese Society of Soil Dynamics. Professor Finn has also received the Quigley and Meyerhoff Awards of the Canadian Geotechnical Society, the Low and Leggett Awards of the Engineering Institute of Canada, and many others that I'm not going to list right now because I know you want to hear Professor Finn. So would you please join me at the podium, Professor Finn? Thank you very much. In recognition of your contributions to geotechnical earthquake engineering, I present you there's a check in there, I hope.
It would be indelicate to look.
And the 2014 H. Bolden Seed Medal.
It's the bronze medal.
Thank you.
Thank you. I'm very happy to be awarded the Seed Medal. It means a lot to me personally, as will become evident when I begin my formal talk. It's a great pleasure for me to look out and see all those faces. One half an hour ago when I came in here and I saw this huge empty room, I said, my God, will anybody show up? So I'm very pleased. And I'm very pleased to see so many young people. That bodes very well for the future of our profession. Now, my talk is not in the proceedings or in the disc for a very good reason. When I got my letter telling me in November that I had been given the Seed Medal, there was no mention of giving a talk. I knew talks had been given, but I was not at all averse to taking my medal without a talk. So I didn't say anything. Then, about 5 weeks ago, I had a charming letter from Helen Cook saying, I'm horrified to think that we didn't ask you what the title of your paper was. And I sent her back a very friendly note saying, I was horrified to hear I was giving a paper. So I asked for 3 days to think of something to do. It had to be something that could be packaged. I wouldn't dream of demeaning the Seed Medal by not doing the best I could, but a sharp technical talk simply wasn't on the cards. I'd have to drop everything else I was doing. So I gave this general title, Developments in Liquefaction Triggering and Consequences. And with a reasonable, friendly interpretation of that, that's what I'm going to do. That is a rather unusual photograph from the 1983 Nihonkai Chuba earthquake in Japan. 2 days after the earthquake, water is still being pumped out of the ground. Now, how was I going to start this talk? And then I came across this charming vignette from New Zealand television, and it gave me some ideas. The young lady, I hope, will be in full voice.
Now, seismologists claim that much of the damage that's been caused across Christchurch has been caused by a phenomenon called liquefaction. A couple of days ago, we had never heard of that term, but everyone speaks about liquefaction, and indeed, you can see it everywhere around you, because this quake was relatively shallow, just 5 kilometres below sea level, and what it's meant really is that a lot of that soil has turned to mud. Carl Eberle has the details on this story.
In just moments, roads turned to quicksand, swallowing cars and swamping suburbs.
Oh, it was straight after the earthquake, mate. It was frightful.
This process, called liquefaction, has left much of the city a soggy, crumbled mess.
But the liquefaction, I mean, the suburban streets are like rivers.
You'll see these ladies over here, they're just sinking.
The silty, saturated layers of soil just below Christchurch were so severely shaken, they liquefied.
So I thought, after working in this business for 50 years, if people are still saying, what is liquefaction? I thought maybe we should recap a few basic fundamentals. Now, here we have a deposit of sand, very loose and saturated. And when it is shaken, two things happen. The sand structure tends to collapse, push the water out. The rate at which it does that depends on the pressure and the density of the sand. But the other thing that happens, when it's all over, you get settlement. Now, I'll show you a few slides that illustrate that. The first slide I showed you was a classic example of that, and I have a couple of more. This is how Professor Idris and his colleagues identify liquefaction at sites when they're compiling their database. But it makes a big difference what actually is the indication. This suggests to me that whatever was happening was pretty shallow, the pressures were not great, they didn't eject very much, and the rest of the structure of the field, which is a tobacco field, by the way, is pretty steady. Now, on the other hand, if you come to this one, the sand was ejected with explosive force. There was a fairly stiff layer overlying the liquefied material. The pressure had to build to a very high level to get out, and it suddenly just popped everything. So you see two sources, one here, and that is about 2 meters. And all that sand was deposited as a result of the ejected material in essentially one blast. In the northern part of Japan, around Noshiro and Akita Port, there were warehouses along the dock in which the floor had been blown up, and inside the warehouse was a huge mound ejected from something like that. So it's a very powerful phenomenon. Now, this is a much more surface phenomenon. In part of the field is very loose and it's settled, and there's nothing very special about that. But you can see that when we identify that a soil liquefies in the charts that we use, we're not sure what the story is behind that. There's very different stories behind all of these, and that makes interpretation difficult. Now, this is the iconic picture from 1964 Niigata. These apartment buildings were built along the banks of the Shinano River and reclaimed land. Most development in Japan is on reclaimed land. And when the soil liquefied, this became a very unstable ship. And it tipped over. You can see what a shallow foundation it had. I'm not sure that we'd be satisfied with that foundation even if we didn't have liquefaction. I tend to use this example for my students when I tell them that you have to worry about balanced design. No point in designing a fortress-like structure with a lousy foundation. And on the other hand, there is no point in over-designing the foundation beyond the requirements of the structure for survival. These windows opened after the earthquake. If you go into a new house in North America, the chances are the windows won't open. And people got their furniture and they walked down the face of the building. Now, the other thing that happens when you have liquefaction is that there is lateral spreading. On gentle slopes, it goes on for a while, peters out after a while. But if you're close to a river or a deep ditch, then the very extensive movements can occur. This, in 1988, well, before I published in 1988, but for a couple of years before that, there was a committee in Japan, went back to Niigata, and examined the aerial photographs taken before the earthquake and ones that were taken after the earthquake. And by means of the corner of roofs, the location of the corner of the roof, so-called sharp point, they came up with these strain diagrams for the motions that occurred around the Shinano River. This is roughly where those apartment buildings were in this area here. Now, there's a bridge here called the Showa Bridge, and there was very significant movement at that point, and it damaged the bridge, as I'll show you in a moment. But over here, there was about 10 meters of movement into the river. Now, that had some interesting repercussions after the earthquake. There were some legal questions as to who owned what. A 10-meter plus in a Japanese lot is an unheard of thing. So there were arguments over who owned what. Now, the Showa Bridge, the bank moved in. The top was held by this deep girder, is tucked underneath, and it caused great damage to the bridge. They managed to prop it up and fix it. Now, this one is from the Kobe earthquake, 1995. Around here, there isn't much room to use my mouse here, it's awkward. Around here, the movement was about a meter, sometimes a meter and a half, into the river channel because the stuff liquefied behind the sheet piling. That caused this bridge deck to move in this direction, and the restrainers were inadequate to hold this, and it fell down. The only casualty was a truck driver who was on the thing at the time it fell, and he was killed. Now, the other thing that's of great interest to us is what happens to pile foundations when the ground moves. Especially in port structures, that's a very important issue. The Japanese took this particular example where you have a layer near the surface that does not liquefy. You have a liquefiable layer and then a layer that does not liquefy again. So the pile is sandwiched between two layers that don't liquefy, and there's a lot of movement to the right or to the left. On the basis of a lot of case histories, they came up with a way to analyze that, to put these forces on the pile foundation, passive pressure up here, about half of the vertical pressure along here, and then just analyze the pile and see what happened. That's used by one group in Japan, I think it's the railways, but it's not universally accepted. Now, when I was in Japan, I was on retainer to one of the construction companies, and they built apartment buildings around Western Japan, all of them on reclaimed land. They were supported on piles, concrete cast-in-place piles, minimum of 1 meter in diameter, more likely 1.5, 1.2, one pile under each column. And there were questions about how deep do you have to bring down significant reinforcement in the cast-in-place pile. And so we had to study that problem, and here is a case where you have a layer, just like I showed you, that does not liquefy, a fairly stiff layer. This is a soft layer, but not liquefiable, and then you have a stiff layer again. So to convince them that there was a need to carry reinforcement down the pile, you can see where the large moments are accumulating, and they're about the same size. One is at the underside, and one is very close to the layer at the bottom. So that convinced them that they should not start cutting off the reinforcement until they were well down into this material here. This is a column carrying its share of the load for a 10-story building. and we analyzed it as a stick problem. Now, here's some piles that were pulled in Niigata in 1985, I think I was there. They were pulling down one of the buildings that survived the Niigata earthquake. They pulled out the pile foundations. They also found that some piles had disappeared. They couldn't find them. But this pile, this was at a junction between liquefiable and non-liquefiable. And you can see the effect of that sharp moment had on that pile. Now, one thing, one has to be very careful about case histories on pile foundations from Japan, because most of the case histories involve piles that were not designed to resist seismic loading. They were designed only for controlled vertical settlement. And you can see this type of reinforcement is typical of those piles. Now, over here, where we do design our piles for lateral loading, you get a very false impression of the survival rate for your piles if you were overly influenced by the Japanese case histories. This is Tom Rourke from Cornell. We were together on this occasion, and this is a nice sheared off pile. The other part of the pile is right here. But again, you don't see any dense reinforcement. Now, I found this one. I was on a crane rail, and I wondered what was happening to the pile so I leant over, and somebody hold my legs, and I went over and took this picture. Now, this as movement is about little over a meter. The soil has come this way, flowed past the pile, no apparent damage to the pile. Now, this pile was designed to carry crane loads. So it had a horizontal component in the design. And they also put in a steel pile, of course, which had a much better survival rate. So when some lateral loading has been built into the system, those piles behave quite well, actually. Now, this is an example of, I took this because I wanted my students to see if they could figure out what the pressure of the liquefied soil was based on the yielded shape of that pile. I can't remember now how successful they were compared to what theory would tell you, but I think they were pretty close. Now, so much for a warm-up. We know what liquefaction is. We know what the problems are. Now let me take you back to the very beginning. It's 1964. 2 earthquakes have occurred. One, the Good Friday earthquake in Alaska, the June earthquake in Niigata. A big problem in both was liquefaction, wholesale liquefaction, flow slides, you name it. Now, an urgent problem in Alaska was reconstruction. And of course, most of that stuff had to be mortgaged. Mortgagees wanted to know, how safe is it to rebuild there? Shannon and Wilson in Seattle were commissioned to supply the advice that was needed on that topic. Stan Wilson was a very, very clever engineer. He knew that this was going to pose new problems for him. Testing up to date would be inadequate to test the response of soils under cyclic loading of the earthquake. Liquefaction, nobody knew anything about it, except later on they looked back and saw it happened also in 1906, but nobody had studied it from a technical point of view. So Stan Wilson had his friend, Harry Seed. They'd been to Harvard together. Harry was in Berkeley. And furthermore, Harry was carrying out pulsating load tests for the State Highway Department. Where you put the load on, you lift it up. But you don't pull the sample both ways to imitate the effect of traffic loading on a base. So that seemed like a great start. So Stan Wilson called in Harry Seed. And Harry Seed was very fortunate. He had 2 very bright graduate students, Ken Lee from Alberta, and our one and only Eddie Idris. Now, fortunately, they had diverse interests. Ken was a good lab person, so he looked after the liquefaction testing. Ed was creative, a man of ideas. He still has a few. And he was on the analysis side, and I was impressed. Ed started out big. He started analyzing the L Street slide in Alaska. That was a huge slide. Now, he was helped by the fact that a graben formed behind it, so he knew that he could look at segments of it. And he was interested in what the strength was underlying that and how the seismic forces were driving it. Ken Lee, meantime, was beating his brains out, trying to liquefy a sample using pulsating loadings, and it wouldn't cooperate. About this time, I had been invited in 1963 to come to Berkeley as the visiting professor in 1964. Harry invited me personally. And so I arrived on the scene just as this work was getting underway. And I saw how little anybody knew about this field, so I said to myself, what the hell am I doing in plasticity? Which was my field, and I was going down to give lectures on it. And at that time, people knew a lot about plasticity. There were some world leaders at Berkeley, like Nagdi. There was Prager back at Brown University. I was just a humble graduate from the University of Washington. But I thought, this is great. I'm going to get into this field when I go back. So I paid strict attention to what Harry and his cohorts were doing. Now, Ken Lee was lucky. One night, something went wrong. Instead of pulsating, the load grabbed the head of the sample and turned it into a cyclic load test. And it liquefied. So Ken was taken care of. He spent the next couple of years testing Monterey sand and Sacramento River sand, finding out what variables control liquefaction, giving us a deeper understanding of what it was all about. Now somebody's got to do something about that. Now we know what stresses will cause liquefaction in the sand of a certain density. In those days, the CPT was not in the game, or the SPT either. So now it's Ed's turn. He has to find a bridge between the stresses and the strength. And so he came up, laid the foundation for what is known today as the simplified method. And it was quite clever, actually. Here's the equation that he used. He assumed that the soil was rigid, so the same acceleration applied at any depth. You calculate the shear stresses, that's the first part of that equation. But then he wanted to take into account the fact that the motions actually decreased as you went down. So he put on a factor to take care of that. And then he realized that big earthquakes shake the thing longer than weaker earthquakes, so he put in a factor to take care of that. Now we're ready to go. That was the beginning of the simplified method. Now, the weak part of the whole system, although it took some time it took a year or a couple of years probably to sink in, was that you couldn't get samples to test in the laboratory. If you tried to sample a sand that was potentially liquefiable, it densified, and so you couldn't test the sample as it was in the field. So another method had to be found. Now, there was a hint of what to do in the first reports out of Niigata. A guy called Osaki, he plotted all the locations for which they had SPT data and whether liquefaction occurred or not. And he found that there was a line that separated the two. And he said, for Niigata, for the kind of ground motions we'll have here, the earthquake magnitude 7.5, ground motions between 0.2 G and 0.3 G, this is a good criterion to judge what's going to happen. But there was no way of transferring it anywhere else, because it was just for one set of circumstances. Now, Professor Idris's technique allows us to evaluate the thing for almost any earthquake, what the stresses would be. But we need more field data on how the SPT identifies resistance. Now, Bob Whitman did some work on that, but he had a very meager database, up to about 75, I think. No, about 70. Then Harry took it over with the help of Idris, and they brought it up to a paper that Harry wrote for the Centennial Conference in Philadelphia in 1976. It's a very long paper. Took him a long time to get ASCE to agree to publish it. He was not quite God yet. But eventually it was published in '79. And that set, now we're set. We have a standard of practice that engineers can use. They don't have to test in the laboratory. They get their resistance from the SPT in the field. They use Idris' simplified method to calculate what's going to happen. Now, the next thing that happened was that, not about the next thing, but one of the things that happened was that NSF decided to fund a group of people who were active in this area to get together for a couple of days back east, have a seminar on this thing, come to some consensus, and produce a written report. So in 1985, the NSF volume came out, and it was quite an advanced text for its day. It had the simplified method, it had the SPT approach, it discussed soil testing, and it had analysis in it. In 1975, Harry Seed, Jeff Martin, who gave the 2012 Seed lecture, and myself, we developed a soil pore pressure model so that you could predict what happened when a soil sample was loaded. I had a very bright PhD student at the time, Michael Lee. He put that into a program, and I also decided to put into it a dissipation model so we could develop the pore pressure and allow it to dissipate as well if it wanted to. We produced the first paper at the Denver Conference of ASCE in 1975, but nobody was interested. Nobody was interested. Then we continued to develop that. In 1980, I had a 2D model. And then early in the 80s, I began to use that in British Columbia on tailings dams. And that was followed by embankment dams for the Corps of Engineers and some overseas work. But the profession as a whole was not interested in effective stress analysis. And it's understandable. Now, while this was going on, the Europeans began to marshal their intellectual efforts to develop constitutive models for effective stress. They were all based on plasticity theory. There are many of them. Then in North America, some of our schools began producing these too. Davis had a particularly good model by Yanis Stefelius called the bounding plasticity model. It was for clays, not sands. And then a whole industry sprang up. In Japan, in Europe, and here, we now have, I would conservatively say, at least 100 constitutive models. They're all good because they were all published and they had to satisfy test data to get published. But again, nobody is showing any interest. Now, the one thing that did surprise me was that Berkeley, after, I may be running ahead of myself here. Let me stop at 75, at the time Harry and Martin and I developed that model, because this was a unique time, actually. The state of the art coincided exactly with the state of practice. The cyclic loading testing, liquefaction triggering. Now, there were two programs developed that were very useful, SHAKE by Seed and Schnabel, and Quad 4, in which Professor Idris made a unique contribution by introducing variable damping in every finite element. Everybody was satisfied. It was like the Roman Catholic Church before the Reformation, and Harry was the Pope. And all that was due to the group at Berkeley. I have to give them full credit for that. Thinking about that last year at the Geo Congress, when I gave a paper on something else, I recognized the three guys that I thought had done all that. I think I'd like to read it if you don't mind. This paper is dedicated to three men who laid the foundations for the development of geotechnical earthquake engineering in the 1960s and nurtured its growth by major contributions to teaching, research, and practice over many years. The late Professor H.B. Seed of the University of California at Berkeley and his PhD students at that time, Professor Ken Lee of the University of California, Los Angeles, who died very young as a skiing accident, and Professor I.M. Idris, recently retired from the University of California at Davis. And there's no doubt about it that that small group put practice on the map. In a record 10 years, everybody was doing it. Everybody had control of all they needed to do a good job. Now, the developments from 75 to 95 were roughly what I was telling you about: nonlinear total stress analysis, nonlinear effective stress analysis, but nobody was paying too much attention. Residual strength becomes a real problem, and it's costing a fortune. What strength do you have to resist deformations after the soil has liquefied? And assuming that you do get some significant straining. What is the strength? Well, the easy answer is measure it, but you can't measure it because the circumstances under which it is developed are not known. Most sites have mixtures of sands and silts, high permeability and low permeability materials. If you have a layer of sand bounded by impermeable materials, when the sand liquefies, it's going to settle. Water comes to the top. In theory, if that were a continuous surface, you'd have no strength at all. But what happens is that once that water develops, cracking develops. That water seeps up out of there. Now you have a different structure entirely. And we don't know what the strength there is. And it was Harry Seed's final great contribution, in my opinion, that he decided to try to get this strength by analyzing case histories. It was a very difficult task. The case histories are few in number. The relevant data was hardly available. And the big thing that this showed was that the strengths he measured were far below what you'd measure in those materials in the laboratory, in most cases. So what do we do now? Well, the answer is we tend to use a correlation by Seed himself, then followed by Seed and his son, and Les Harder, and more recently, Idris and Boulanger have proposed an extension of that data into slightly stronger material. But it's very conjectural, all of it, but it's costing a fortune. By going by the lowest value all the time, it's really costing a fortune. Now, returning briefly to the simplified method. Over the years, Professor Idris has continued his interest in that topic. He's updated his database on many occasions. And then finally, it culminated in 2008 in the publication of his text monograph, EERI monograph, with Ross Boulanger, another Canadian, by the way. Now, I spoke about that book at a Prakash conference the year after that in San Diego. I consider that book to be one of the classics of geotechnical engineering. He reviewed the whole research worldwide on that topic. Of course, he explained his own method fully because he knew it best. But that is a monumental text, in my opinion. It will survive for a long, long time. In the meantime, Ray Seed had developed his approach to this problem. Now, both methods were out there for a number of years with no hassle, nothing. Some of us who had to work with those found there were differences. I found the big difference for dams, where you had to look at liquefaction at great depth. They gave very different answers down there. And you had to reconcile that in some way when you were doing a job. But consulting engineers found ways of dealing with that. They also used Youdd's method, which represented practice up to 2001, and between the three of them, they picked something they could live with. Then ERI put a match to the powder. They sponsored a series of seminars on the book. And Professor Seed considered that an unjustified endorsement by them of one method. So it was a very difficult time for everybody, especially for Professor Idris and Professor Boulanger, who had to maintain composure under provoking circumstances. Finally, the government agencies, state agencies, began to get concerned about what to do. Uncertainty doesn't fly in those agencies because heads roll if they make a mistake. So ERI finally decided they better do something about it. They set up a small committee. Tom O'Rourke was picture I showed you earlier, myself, Les Youdd, and Kramer in Washington, asking our advice on what should be done. And we decided the only sensible thing to do was to set up a committee, a powerful committee of the profession and the researchers, and sit down and decide what is an appropriate state of the art for this time, just like they did with Les Youdd in 2001. They adopted that suggestion. That committee is now meeting. There's a big meeting in Arizona on March the 10th. Professor Idris will be there with Professor Boulanger to present their thing. By the way, this committee is not going to decide who's wrong or right. That's not the point. They're going to listen to both parties, but they're also going to review other things and decide on a consensus, hopefully, state of the art that we can all follow. Now, leading up to this, Idris and Boulanger went over the database again, and they produced two new documents, one on SPT, one on CPT. And these documents are invaluable for the attention given to the database in both cases. Everybody should be familiar with those two. Now, I'm going to read you two warnings here. In the 80s, there was a fashion to introduce international test standards for calibrating constitutive models. The first, in 1988, was based on tests, laboratory tests. So the designers were given what they said they needed to calibrate their models for any eventuality, mostly triaxial and consolidation. That's what they asked for, that's what they got. Then they were asked to predict the performance in a different stress path and also in cyclic loading. And the results were not encouraging. Now, the next thing was 1994, when we had VLAX. This was the next step in evaluation using centrifuge tests. Now, centrifuge tests are in fact the ideal way to do it. I suppose it makes sense to calibrate your model on the element test first, but the stress states are homogeneous, and in the real world, they're inhomogeneous. And the centrifuge allows you to develop inhomogeneous stress states. So they had to go at that. Again, it was dismal. Now, it's interesting to see what Smith is the guy who wrote a very fine book on finite element analysis, very knowledgeable guy. He was asked to comment, and he said, a particularly insidious feature of the calibration process is that the predictor could calibrate his/her model to fit the bulk of the largely triaxial data provided in the information package and still make poor predictions of seismically induced stress paths. The same problem that happened earlier on with the laboratory test exercise. And the problem is that the models are path dependent. They can't follow. The assumption had always been they could calibrate their model, especially the plasticians, could calibrate their model by triaxial and consolidation tests, and then go in any direction they liked. There'd be no problem about it. But that didn't happen. You're forced, really, to calibrate your model, if at all possible, along the dominant stress path in the problem you're trying to solve. You're never going to get it right. If I was interested in the rocking of a foundation, I would use triaxial tests. When I'm doing an earth dam, I use shear tests, direct shear tests. That's a very narrow one too, but at least it's moving in the right direction. The problem, we have the old problem. You could induce in the laboratory using hollow torsional tests, any stress path you want. The trouble is you can't get an undisturbed hollow cylindrical test. You can only study the parameters that are important, you can study the physics of the problem, but you can't do the job you're getting paid for that way. That's the real problem. And it's always a problem. And that's why when you are doing analyses of a dam or something like that, it's a very good idea to use two different analyses. We recently did a job for BC Hydro. We had two different analyses, and we got two different answers. I wouldn't say they were critically different, but they were significantly different. And you have to rationalize those things when you get it. My advice is never let an analysis override your instinctual judgment as to whether things are right or not. Now, this is how the latest effort from Professor Idris matches what Youd was doing. They're pretty close, but these are for shallow depths. Now, and for 7.5 earthquakes. Now, there's one thing which I'm going to talk to Professor Idris about when I have a chance to talk to him privately. This is his curves for the CPT data. One of the pioneers of that method, Peter Robertson, is here. You should talk to him. He's a pretty sharp guy on this one. I don't care for velocity very much. I find the change here too abrupt between being in deep trouble and having no problems. There just isn't enough room there, in my opinion. I'll be coming to you in a moment, Dr. Stokey. You are not forgotten. Now, the one thing I would like to draw to the attention of those of you who are in practice, or in research for that matter, and that is that when you're processing the data from a seismic cone or whatever, there's great software out there. This is the stuff here. This thing does about if you believe the model that's used to calculate these various things, you've got the answer you want. If you don't believe that, try a different model. But the processing is difficult, impresses the hell out of clients, these lovely colors, and you can see how it all comes out in the wash. You have your CRR resistance line, you have the demand, you have the factor of safety. We like to use liquefaction potential also, which is we weight, once we've got the factors of safety, we like to weight them. The ones near the top, we weight them as 1, right at the bottom is 0, and we vary it linearly in between. The idea being that a liquefied layer at the top is a hell of a lot more trouble than a liquefied layer at the bottom. And we don't want the deep liquefied layers over-exerting influence on our design. Now we'll pass Dr. Stokey quietly this time. Now, I'm involved in a school project in British Columbia. We're retrofitting 800 schools over a 15-year period Cost estimated so far at $2.5 billion. Now, the way it works, after a shaky start, the government decided that they would make an allocation every year to the University of British Columbia, $1 million, to do the research into retrofitting the schools, both the geotechnical research and the structural research, to come up with efficient, cost-effective methods of dealing with the problem. The rest of the money goes to, of course, retrofitting. But they also established a technical review board. At the moment, there are 25 engineers on it, 5 of whom are geotechs. The school has to come up with a plan for retrofit. And if they have a liquefaction problem, they have to decide how they're going to do it. They don't do it yet, just how they're planning on doing it, and so on. Now, this report goes to the technical review board. They look at it to see if the school followed the guidelines. And if they didn't, they send it back. And if they don't confide, they don't get paid. They don't get any money. So there's a very big whip there to keep people in line. Now, one of the things that we've been looking at is characterizing the site of the school. Some of these schools are very big and very difficult to sample and all that. So we looked at ambient vibration, Dr. Stokey. Not SASW, but ambient vibration. And we have a system now, we can go down 100 meters, and you can see those points in between. The fill points, they're SCPT, the open circles are downhole, and the blue band with the jagged line is the average from the ambient vibrations. The system we have takes the dispersion data, runs 100,000 Monte Carlo simulations, get the mean and the standard deviation from that. And that's what you're looking at here in the color. And so there's only about a 5% difference between doing it the measured way and using ambient vibrations. And this is the prediction for a number of these sites using the measured data. And this is the prediction using the ambient data. The yellow points are the ambient data. It's very good, and it's very fast and very cheap. So we'll be using that more. Now, here's something that I want to draw to your Dr. Idris's attention. He's come up with a new magnitude scaling factor, which increases the potency of earthquakes below, let's say, 6 to cause trouble. And in Canada, that's an issue. Because in eastern Canada, most of the earthquakes are in that range, not greater than 6.5 mostly. But in his latest publication, he has a new set of magnitude scaling factors, some of which are smooshed. Drop it down even further. So that is of some concern to us, and I was hoping he'd be here. I would talk to him about it. And there he is in the front row. Now, you can see the difference it makes if you go to a magnitude 6. You see, this would be what you would get from the old MSFWs. This is the new one. So there is a difference in the factor of safety. And that can be significant, but of course it's irrelevant if it's correct. Now, the other remaining challenge, is probabilistic ground motions. In Vancouver, the design acceleration for site class C is 0.46 G. Now, if you're looking at liquefaction, what magnitude and acceleration are you going to use? Well, until 2007, they were saying, well, we'll pick one of the bigger ones, 7.3. We'll associate 7.3 with the full probabilistic ground motion. And that was very hard on the system. Now, we did a study, a guy called Whiteman and myself, in 2007, showing that they shouldn't be using 7.3. They should be using, if they were using the full acceleration, they'd be using the average value, about 6.8. In the next edition of the guidelines that are circulating for use in Vancouver, they compromised and dropped it to 7, which is still too high. And these changes, these underestimations of factor of safety, are very critical for lateral spreading and for settlement. So this is what contributes to the NBC in Vancouver. All of these earthquakes. Now, these earthquakes contribute different amounts, and this is the percentage that each magnitude contributes. The biggest magnitude contributes 16%. Now, way back in 1984, I attended a World Conference keynote by Professor Idris, and he addressed this issue, and he suggested that we should weight the magnitudes by the amount of their contribution to the probability, and then run a hazard analysis, and you would get a liquefaction resistance curve for whatever magnitude you decided to adopt. So we did that, and we did it for a 7.5. It doesn't matter what you do it for. It doesn't matter. Whatever you do it for, you will get a liquefaction resistance curve such that if you enter it at the right probability, you'll get the acceleration that you should use with that magnitude. Now, there's nothing, that's child's play. The only problem is you have to run the analysis. Now, in Canada, you can probably send your weighted magnitudes to the GSC, and they might run it for you. At the university, we subscribe to Easy Frisk. We have a license for Easy Frisk, so I use that. But, I mean, this was a very bright idea way back in 1984, but it's only recently that people are beginning to realize how useful it is. This shows the difference in factor of safety between doing it using Idris's suggested weighted magnitude method or using the mean magnitude of 6.3. There you go. Now, all the other suggestions, 7.3, 7, and so on, they're all down here. You have a very substantial difference in the factor of safety. You're underestimating it badly. Now, if you're going to do lateral spreading, these are based on the methods of Robertson and Zhang, Seed's LDI method. They're all based on shear strain, maximum shear strain developed or allowed to be developed in the case of Seed, and the factor of safety against liquefaction. So when you enter one of these curves, if you're here, and you come up, say you have 60%, you're up here, you have a maximum cyclic shear strain of over 20%. That's a whopping number. Now, if you add 2 to that, you're over here, and you're up to about 10%. That's half. So you can't toss these fractions of factors of safety away just because you don't want to do a proper probabilistic assessment. Now, in the same way with settlement. Settlement is calculated using Ishihara's method, and when again, what do you find? You find you're depending on the factor of safety, which gives you the shear strain, which gives you the post-liquefaction volumetric strain. And if you are down in this area where they drop sharply, and you move 0.2 units of factor of safety to the right, you cut your stuff in half. These are studies we carried out on the Delta in British Columbia for another purpose for the government. Now, let's come to one that's very commonly used and misused, Youdd's method for getting lateral displacements. We have his equation. I'm not going into that. Now, this is the operating thing where Les is concerned. So Les drew this chart, and for different magnitudes, he gave the average acceleration, peak acceleration, as a function of distance. And this is for site class D. And it's the average of, I think, 3 or 4 attenuation laws. Now, he said, if you have an acceleration, you come in here, you come over here, read off the magnitude, and put that magnitude into my equation. And the distance. So if I have a 0.4 g, say Vancouver around 0.46. You come up here, if I'm about 10 kilometers away, I have to have a magnitude 7.5. If I'm very close, I can have a small magnitude. Now that's fine. How do you get the average acceleration when you have probabilistic ground motions? How do you handle Youdd's equation with probabilistic ground motions? Well, the first way to do it is to do what we did earlier on for factor of safety. You take each magnitude at various distances. You get this information from the Geological Survey. You show how much that magnitude contributes to the acceleration at those distances. Then you calculate for each of those distances, you calculate Youdd's displacement. And you add them all up. So these are all displacements for different magnitudes at different distances. You add them all up horizontally. That takes care of the contribution of each magnitude, and then add them up vertically, and we find out that you have a settlement of 0.58 meters. 0.58 meters. That's the way of doing it. It's the first time you do it, it's an Excel slog, but after that, it's not. If you have the information, it's okay. But the other way to do it, which is very easy, again, if you have a hazard program, to get the average acceleration, what I do is I calculate the acceleration, hazard acceleration, with the epsilon equal to 0. That is, no variation about the mean, because the probabilistic ground motions are calculated using a normal distribution about the mean. And how far you are from the mean is measured in terms of standard deviations, epsilon being the number of standard deviations that is used at any particular time. Now in Vancouver, the average epsilon is 2, which means that to get those probabilistic ground motions on the average, it's 2 standard deviations. It's a long way from the average. So we toss out epsilon and we get the average acceleration, go into Les Youds with that, and what do we get? We get 0.49. It's very close, not quite the same, because we use a much finer mesh when we're running the hazard program than we are when we're running the Excel, for obvious reasons. Now, there are different methods. There's Bartlett and Youds, Robinson and Zhang, and Idris and Boulanger. You can see the difference, very substantial difference between them. Now, Idris and Boulanger, that is LDI. They don't claim that that's the lateral displacement. It's an indication of whether you got a serious one or not. So perhaps to some extent that's misleading to have that in there. This is for a school in British Columbia. Now here's a school in Delta, and this time we're using the average acceleration method, the de-aggregation method. See how close they are, those two. And then this is Youds. And with Youds, we're using what they say should be the acceleration in Vancouver on this particular site, if you'd calculated using Shake, 0.35 G. And that's very, very much higher. So there's a lot of uncertainty in the calculations, but you also have a lot of errors depending on how you calculate them. You have to follow the rules of the method as explained by the author. And you have to have as precise an indication of what's going on as you can possibly get. And that means you don't get careless when you calculate factors of safety. If you use the de-aggregation method or Idris's weighted magnitude method, you will have a very accurate assessment. Given the rest of the data is okay, you'll have a very accurate assessment of what the factor of safety is. If you arbitrarily stick some magnitude in because you like it, with the probabilistic thing, the chances are you're underestimating, costing yourself and your client money. I want to close the loop. Now, the school thing, when the geotech does his job, he calculates all this stuff. Let's hope he calculates it right. If he doesn't, we send it back to do it again. The structural engineer has his building ready to go. Now, what's going to happen? Does the geotech decide I'm going to treat the liquefaction using sand drains or compaction grouting or jet grouting or whatever you want to call it, or not. In the beginning, they were doing that, and it was costing a lot of money for two reasons. You can't compact under a school without pulling up the floors and making the school unusable for about 6 months. To move a small school to a temporary accommodation is $250,000. A big school can be as high as $750,000. That's on top of all the other costs. So we decided, no, they had to come to the TRB to decide what to do. I call that closing the loop. We're forcing the geotech and the structural guys to get together under the aegis of the TRB and hash it out and decide what's the best and most economical way of doing it. And here you go. I'm not going to talk about that, but I just wanted to show it. Since it's not in the thing, we have a manual that describes all of this stuff, Seismic Retrofit Guidelines, 2nd edition, liquefaction. And we're going to have to revise it again now because Canada is going to change the whole set of ground motions for 2015 code. Much, much different than previously. So what does the structural guy bring to the meeting? He says, these are my limits. My LDRS, that is the load displacement resisting system, I cannot tolerate more than 2.5% drift. My vertical exterior loads in this building cannot take more than 1.25%. Interior columns can take 4% because they're steel. Now, okay, so the geotech comes along. Don't tell me I took it out. Well, I guess I pulled it out. Sorry. The geotech calculated the amount of lateral spreading, the amount of vertical settlement. This is the school in question. Now, the drift limits are set up like RD is the residual drift. That's the drift just due to shaking. The residual drift due to shaking, assuming the foundation is rigid. Then we have the effect of the horizontal displacement, drift, I should say. We have the vertical, and they must be less than the allowable drift, total allowable drift. Now here's the school again. Now there's an interior frame here, and this has struts on it. Now it doesn't actually have a tie beam. So this is what will happen to that. This will go down, this will go down, and this puts additional strain on this thing, it may go. So this has to be, this governs now. Now if we put a tie beam in there, that doesn't happen. This will rotate, but now the troublesome parts are the column, not the lateral displacement resisting system. And so here's a building in New Zealand that behaved just like that. It rotated, but it was tied at the bottom and it did not spread. Here's the geotech's input. 140 millimeters differential vertical movement, 600 millimeters horizontally. Coefficient of friction between soil and foundation, 0.4. Bearing capacity on the truss, 50 kPa. Because the first thing that the geotech has to demonstrate that the footings won't punch through into the liquefied material. This gives you just an idea what the school looks like. And here's that beam. The red there shows the beam just put in, and the red vertically is a new tie beam that went in. The steel columns in the interior can take 4%. It turns out that the total drift is 3.8%. The steel columns can take 4%, they're okay. The external column, remember we fixed the LDRS in the middle by putting in a tie beam, that's out of the picture. Now all that's left now is this exterior concrete column. How are we going to fix that? Well, the structural engineer decided to put in a new pedestal, a new concrete pedestal at the bottom, put in a steel column, carry it up to the top, and then brace the whole thing against the roof. And it's over, that's it. No attempt to remediate liquefaction. All that money was saved. All it takes is a couple of tie beams and a couple of steel columns to carry the extra load. The school is not interrupted to any significant extent. You saved all that money on extra classware. Now that's how we work on the school project. And it's not a bad model, actually, for geotechs and structural engineers to follow in the future. There's the finished job, column, steel columns, new tie beams. Now I'd like to acknowledge the help of my postdoctoral fellow, Jason Dowling, who put together the presentation for me, and I want to thank you for your attention.